Select the best set of reagents to accomplish the following transformation. So when we're looking at a synthesis problem such as this, we want to consider what we have, what we're starting with, and what we are forming. And we want to always ask ourselves if the carbon skeleton is changing and if the functional group is changing. And so what we should notice here is that we start with an alkene, and we are also ending with an alkene. The difference is that we appear to be moving the alkene from between these two carbons here to these two carbons here. So to approach this, we want to identify how we could synthesize an alkene. That's our product. So we know that we can do an elimination reaction to get an alkene. And we also know that if we start with an alkyne, we might be able to selectively reduce to get an alkene. Since we don't have an alkyne to start with, it seems much more likely that we're going to go about this using an elimination reaction. So when we do an elimination, we need a good leaving group. And we also want to think about where that good leaving group could be located. So we should notice where our alkene is in the starting material and where the alkene is in the product. And we should note that we have one carbon atom that is in common between those two. So we should be able to introduce a leaving group onto that carbon that we've just highlighted, and then do the appropriate elimination reaction to get the desired alkene. So we want to do for the first step, so we're going to redraw this molecule. And so the carbon that's highlighted is the more substituted carbon atom. So we want to do a normal Markovnikov addition of a hydrogen and a halogen in order to get something with a good leaving group. So if we undergo this reaction, so what we will see is that the hydrogen is electrophilic, so the alkene, being a nucleophile, can attack that, and then we will break the hydrogen-halogen bond. And so this hydrogen is going to be added to the less substituted carbon atom. So I'm going to draw the hydrogen that we started with, and so then we can see that after we've added the second hydrogen, we have two hydrogens on that carbon atom, and the tertiary carbon is the one that is left deficient, so that's where we have a positive charge. And so then the halide, which we just liberated in that first step, is a nucleophile, and that halide can attack the carbocation that we just formed. And then if we want to, now we've got a good leaving group on the carbon atom we want. So if we do an elimination reaction, there's two possible alkenes that can form. We can either remove a hydrogen from this carbon atom and do the elimination. That would bring us back to the alkene we started with. Or we could remove a hydrogen from the end carbon atom. And that's what we want to do because we want to have the alkene between these two carbon atoms. So in order to make sure that we do the elimination from that end less substituted carbon atom, we need to force this elimination by using a large base. So we want to use something along the lines of tert butoxide. So a carbon atom that is very bulky. So we've got a lot of branching right there by the negative charge. So that is a large, bulky base. And so this will remove a proton from this end carbon, pushing these electrons in and pushing off the leaving group. Okay, so the two steps that we're looking for, so we're looking for in the first step to add HX, and we want to make sure we add this in a Markovnikov fashion. Right, and so HX could be something like HCl, HBr, or HI. And then in a second step, we said we want to use a large bulky base in an E2 reaction. And the reason why we're using that large base is so that we can form the less substituted alkene. And so the conditions that match this are B. So we've got hydrochloric acid, which can do that Markovnikov addition of HCl. And then we've got this bulky base that can give us the less substituted alkene product via an E2 elimination.